We're good to go. We're good to go. So I try to be a bit faster so we can all go into the break more or less on time. Thanks for the introduction. Let me briefly repeat because Anne does not have a microphone. So I'm Steffen Bondorf, and this is actually work mostly conducted by Alexander Scheffler. He's a PhD with me at RUB, Ruhr University Bochum, who is also co-supervised by Jens Schmidt from TU Kaiserslautern. And what we mostly do is we look at the analysis of feedforward networks and we try to improve efficiency of analysis. And we often go into the route that we create a heuristic, have a trade-off about accuracy of the analysis. So how good are the bounds and how fast is the analysis? And that's exactly what we did for feedforward networks that employ FIFO multiplexing. And our tool to get this trade-off was a search algorithm. And a disclaimer for those in Zoom, I also deleted a couple of slides because this work was published this year at RTNS, and these are basically the original conference slides that were created by Alexander Scheffler. And I will skip network calculus background for the audience here. I just want to raise awareness to get back into your mind the problem or the challenge with FIFO multiplexing. And here Joyce's book is referenced as given the definition for a leftover service curve in FIFO multiplexing. So basically, we have a service curve and an arrival curve, the arrival curve called alpha 2. And we want to know what's left over after alpha 2 was removed from the server, so the guarantee for the remaining flows at the server. We create this leftover service curve that has a free parameter theta. And this theta parameter, we need to set somehow. And only restriction is that we know it must be larger or equal than 0. And the big challenge is that now without knowing the theta parameter, Alexander created this figure to show you based on a rate latency service curve, the blue one, and this, I don't know, green or red one. It's a token bucket curve in the notation of sigma rho, not RB as we saw before, that if we have this service curve and we remove this arrival curve. So basically what happens is we get an entire set, an infinite set of possible curves. They all have the residual rate here and they have some starting point. Interesting is that after this point in t due to all the theta things, the indicator function, we have these discontinuities. The start of these curves all on this line. However, this line is not the leftover service curve. So we cannot work with that simplification. And if we finally want to have a delay bound FIFO networks, we take the horizontal deviation, meaning we need to find the curve that has the matching discontinuity, this jump as it is called in the paper. So after all, after having done the analysis and knowing all the thetas, and then doing the delay bounding, only then we can decide how to set these theta. So we have basically a symbolical expression of the delay bound that we have to work with. There has been related work on that. Let me briefly go over that. So SFA for FIFO multiplexing is a server by server analysis. I just want to mention it because this at every server gives us one theta for every server in the network. So that really gives you a lot of theta parameters later on to set. Let me just skip this part. It's a repetition of the previous slide. It is quite simple because we can do this horizontal deviation on every server and we can easily find the theta parameter, but as it is server by server, we know we are lacking on a convolution, which brings me to related work, least upper delay bound by Bistis-Dea et al. And 2008 is one of the earliest papers on that. They're looking at nested interference. Nested interference simply means we want to convolve before we subtract. And in this tandem here, that is a nested tandem, what we see on the right side, this flow, it is called nested F2 in F3 because its path is a subset of the path of F3. And then we can simply first subtract the arrival curve of F2 from beta 3, then we can convolve, and then we can subtract from the convolved leftover service curve for servers 2 and 3 the interference of F3. This is basically what I just said, convolution before subtraction. And that has the benefit that we pay multiplexing with cross flows not too often. So we saw pay multiplexing only once on a previous slide by Ludovic. This is exactly what this aims for. And of course, just a repetition. We, in the end, want to optimize for all the theta parameters we create. Question is, how many theta parameters do we create? Is it less than with FFA? It is, because we subtracted per flow. It usually gives us, we subtracted these flows on convolved tandem. So F3 is not potentially subtracted more than once. And this gives us a nice tree representation we brought here. For example, going this route, beta 3 over here is what I just said. The leftover for this flow is the service curve unchanged because there's no nested cross traffic. But for the F3, we first have to take the unchanged service curve we convolve with this leftover minus the flow that went over. So it's simply a tree representation of what I told you. All right, so this is kind of the least upper delay bound for nested tandems. And to scale up to entire networks, what Alexander Scheffler did is he embedded this tandem analysis into feedforward procedure where we look for how to best bound outputs, how to aggregate flows, and so on and so forth. But this is a paper I just want to reference. It was published last year and the code is available online. What we learned from that, because it was basically re-implementing least upper delay bound, is it takes multiple steps. And the steps it takes is, here it is. Starting with the flow we analyze, flow of interest, it's called. Then we look on its path. If there's non-nested interference, what we do is we cut into subtandems. You can cut here and there, and then you have a sequence of nested tandems, and you can then apply the least upper delay bound as shown before. Of course, you need these bounds here, and this is the feedforward analysis part, the step 3, that you compute these bounds. It's done in a recursive fashion. Basically, you start all over until you have all the bounds, and I want to show what we looked at is the steps 5 and 6. Because what the least upper delay bound, as it was proposed initially, and what they held, is that they produce a piecewise linear program, even though the input functions are token buckets and rate latencies. And then this PLP needs to be split up, decomposed into one LP per this token bucket stage they have. And these LPs then can be solved with a solver like Cplex. And then you take the least upper delay bound from that. So that's one of the sources this name comes from. That's what Alexander implemented, especially the Cplex part, because we don't want to implement our own optimization. And unfortunately, it turned out that this part, it takes like more than 95% of the runtime of the analysis on average. So natural question is, what can we do? Can we get rid of the optimization? Can we replace it with something? And this is what Alexander was working on. Published in the paper is a search-based algorithm. It's basically split in 2 parts, what he did. One is called LBFF, called it lower bound, and the other DSFF is direct search, and FF because it was embedded into the feedforward analysis. So what basically happens is, so instead of optimizing a repetition, the set of theta parameters we get per tandem, we just try to do it in a different way. This LB is a static way, and DSFF is a search on top of this LB. I'll show you in a moment. This is the definition Alexander provided. He calls it lower bound on the thetas, which is defined as that, which is basically the horizontal deviation. So we're looking for a good starting point for the thetas, and not only starting by setting them all to 0 or something trivial. So as we will delay bound in the end, for every part in this nesting tree, we just set the theta parameter according to what would the delay bound look like for this flow that defines the subtraction. But overall, with all these connections, these interdependencies of flows, this does not provide the best setting for thetas. It provides a valid setting because all theta settings are leading to a valid bound, but it can be improved upon. So this static way is basically the starting point where we put the search on top. So if you look at this slide, it's a repetition I want to skip briefly. So LBFF here, it would have a look. This is the flow we know we subtract. So we take the horizontal deviation to set this theta bound to have an initial non-zero starting point. The more interesting part comes here. So we started, as this is a restriction of least upper delay bounding, with token bucket rate latency functions. And to get a feeling for how the problem shape is for this scenario, we just put a grid over it. So we have set the 3 theta parameters that are the 2 to make a 3D plot, theta 1, theta 2. That's why we removed this flow to get 3 dimensions. And here's the delay bound. Putting a grid over it, we see this has really a nice convex shape. Note that this axis here starts at 60, not at 0 like the thetas. So if we started with theta being all 0, we'll something like here, far away. So we would have a long way to find an optimum. Our LBFF initial setting sets us closer to this point. That's capital theta LBFF. That's why this is that combination. And then the directed search slots. It has, and here I want to cut short, simply 2 phases. The first is an exploratory phase where you see in this current environment, this current setting, we're looking for how to set the parameters to find the direction in this convex problem space. This is done with some step size and checking how changing an individual theta parameter in this setting would get us a better delay bound. So you see there's the interdependence from always re-evaluating our symbolic term for the delay bounding that we derived with the tool. And after we found the direction, the next step is called pattern move phase. It simply says, once we have found the direction, we go this direction in multiple steps. We increase the step size until we overshoot, meaning the delay bound increase. So imagine coming from here and jumping there. Obviously something didn't work out because the delay bound increased. But at this point, we cannot know how close we are to this optimum. Therefore, going back to the exploratory phase is subject to reducing the step size. So we move close to where we want to be. We then overshoot it. So we reduce the step size to take smaller steps towards the goal. And this is exactly, we're scaling here with some parameter. And this is exactly where we can introduce our trade-off. So how much effort versus how good the bounds or how much accuracy we achieve. We just defined a threshold for the step size, and when the step size becomes too small, we just stop, because oftentimes the smaller steps inching forward to the optimal solution, they just don't improve the bound so much. This is basically how it works. So the idea is quite simple, but if you do it in a too naive way, it is quite costly as well. Therefore, and these slides I want to cut short, Alexander implemented some improvements regarding the runtime. It's like selections of where to go, and another one is where to early terminate with the step sizes and so on. Details are in the paper, and by the way, the paper is Creative Commons freely available. So we have this algorithm now to find these three parameters. And we have this step size, and our empirical evaluation is concerned with finding a suitable termination criterion. So what we did is we have some setup with random Erdős-Rényi graphs with flows, and we have a total of like close to 4,500 flows evaluated. As seen before, we have token buckets with unit size, burst, and rate. And just for simplicity, we have set the initial latency of the service to 0. What we changed is a bit the utilizations of something we saw before as well. And now without any further ado, we have results. The metric you use for results is how far we are from the best analysis, best not being the entire optimization, but the LUDB that optimizes these theta parameters. And our metric is just the difference divided by the better analysis. And what's to see is, as said, as we don't have any PMOO effects in SFA, this is really not competitive. And also setting this lower bound in this kind of naive way, choosing the local node flow local delay bound, it's not too good either. On top of that, of course, on top of that, the smaller the termination criterion here for the search, the closer we get to the optimization result. And we clearly see what I just said before. We really decrease a lot, but we don't gain that much. So there's a mismatch. Empirically here, we'd say these are good candidates for setting a epsilon, but of course, there is more than just I forgot to say, I think the average deviation. We also have CDF, lots of that, seeing how it looks like. And 3 to 5, here, you see this termination criterion has from the optimum too much deviation. So that doesn't look too well. So we narrowed down our potential best choices. I'd say to kind of these two, 10 to the power of -3, 10 to the power of -5. And of course, we looked at the runtime. That's the other part of the trade-off we look towards so often. Here, this red line, I guess, is SFA. And you see this is a base pattern for the network size, how long it takes to analyze all flows. And this lower bound is as fast as SFA. It's even better. So this is a better trade-off than SFA. And then here our searches with decreasing termination criterion size, it becomes a bit larger node on the y-axis, the log scale. What else to see here? The LUDB is this here, the implementation with the slow Cplex. It is even slower than with the smallest, with a very small termination criterion until here. But then even our search becomes less efficient than the LUDB analysis. And last, the other analysis, the one proposed by Anne, not the MILP, but the LP version is here. So it's actually also quite fast, not going through all the network calculus, but if we choose termination criterion 10 to the power of -3, that turned out to be a good trade-off. And that's already the conclusion. So what this work was about is to find an alternative scalable version. It proposed to set and search parameters. And then empirically, we had a look for a good suitable recommendation for termination criterion, how small the step sizes in the search should become, and when it doesn't make much difference anymore, or comes at a too high price. Here are some statistics. Then the delay bounds with this termination criterion are only 0.57% on average larger than the optimization one, and the maximum is at 8.56%. So we're looking at catching this maximum as well. What to do about that, because I think it's a bit too much. This is future work. And here's an outlook. I talked about the PLP being derived despite the curves being token buckets and rate latencies. And this token bucket rate latency restriction is exactly this conversion from to the PLPs. If we have input curves that are more complex, this conversion becomes more complex. Nobody mastered it yet. But as we just evaluate and don't do this conversion, we could go for more complex curves than token bucket rate latencies in our analysis. However, we haven't done it yet. There might be a problem that the nice convex shape might be that nice and convex anymore, but might have local minima. And we hope that the initial setting would get us over the local minima to the global one. And that's it. Thank you for your attention. Please.
So if I understood correctly, LBFF finds a starting point for DSFF, right?
Exactly. It's yeah.
And would that be a solution to, because DSFF replaces Multiplex,
right? So the question is, LBFF finds a starting point, but would it be for the setting of the thetas? But would it be a solution by itself? And the answer is yes, because the setting, the delay bounds are always valid for all settings of theta, but it's far from optimal. And with any static setting, we did not get closer. This was a good compromise to get us a good step close to the setting and have less iterations of the search.
Okay, because the search is performed by DSFF and not Cplex.
Exactly. Cplex is out of the picture with the search.
Would it be an option to use like the starting point of LBFF to vary Cplex?
Cplex, the original version of LUDB, it kind of has a starting point too. It's not the delay bound, but it is what's on the x-axis t plus b divided by r, this minimum latency that all service curves, leftover service curves will have. So that could be adapted, probably that you use our starting point for Cplex, but we haven't done so yet.
Here, what could be a method of what could be factors that can make the problem not?
Basically, I think it's when the curve shapes on.
Can you repeat the question?
Yeah. What might be a reason for the problem to not become convex? So we have no analytical analysis to really prove that it's always convex with token bucket rate latencies, but our analysis, this maximum 8.56% that made me suspicious. That's why I said we want to investigate that. So there, I don't know the reason, but there might one. And a very likely reason is when we go to more complex curve shapes, that these curve shapes will result in a non-convex problem space. There's one in the chat, right?
Are those FF analysis features available in the DNCP?
Yes, they are. So are the features available in the tool? Yes, they are from day one from publication. So just get the newest code base and enjoy running the analysis.
Okay, so then if no other question, thank Steffen and the speaker from the first sections and have a break.
Thank you for chairing the session.